For nearly a century, standard quantum field theory has relied on a massive, unquestioned assumption that the universe is built on top of a smooth, pre-existing, continuous backdrop of spacetime. When we try to calculate particle interactions on this infinitely divisible surface, the math breaks down. The equations inevitably generate self-feeding, infinite feedback loops that destroy the models. This diagram shows what happens. In physics, these catastrophic errors are known as ultraviolet divergences, points where the feedback loops scale up to infinity and the numbers become meaningless. The standard workaround is a mathematical trick called renormalization. It doesn't actually solve the infinities, it just artificially subtracts them to hide the errors and force the equations to function. The Adelic Langlands program approaches the problem differently. It argues that spacetime is not a foundational base layer at all. Instead, the observable universe is a macroscopic rendering, an emergent property generated by something much deeper. That true foundation is discrete. The framework models physical reality as the direct output of zero-dimensional arithmetic code, specifically utilizing a rigid format known as p-adic data. This animation illustrates breaking apart that continuous illusion. By migrating the mathematical foundation of the universe to the compact ring of two-adic integers, the local fields of physics are suddenly confined by hard topological limits. Because the topology is naturally bounded, those infinite ultraviolet divergences literally cannot form. The inherent finiteness of the mathematics organically eliminates the infinities, rendering the entire concept of artificial renormalization obsolete. Translating this underlying discrete code into physical properties like inertial mass requires a highly structured sequence. The program uses a strict three-tiered mathematical mechanism to process the data from abstract numbers to physical reality. Resolving the crisis in theoretical physics requires abandoning the smooth background manifold entirely. We have to accept that the observable universe is actively processed from fragmented, underlying arithmetic logic. The first tier of this translation engine operates across the global Adel ring, a vast conceptual mathematical matrix containing the totality of universal arithmetic. The sheer volume of data in this ring is chaotic. The immediate operational challenge is figuring out how to isolate a single, usable arithmetic state from the overwhelming background noise. To probe this space, the framework deploys a mathematical transfer operator, applying it universally across the entire Adel ring to scan for specific targets. Once a target is identified, we use Cauchy residue calculus to cast a net. Here, a mathematical boundary, a spectral contour, is drawn around a single isolated eigenvalue. The contour tightens, effectively trapping the eigenvalue and physically detaching that specific data point as an independent packet. We define this extracted packet mathematically as the local eigenstate. It is the absolute smallest unit of quantum arithmetic code available within the framework. But this eigenstate is entirely zero-dimensional. It is a highly fragmented piece of non-Archimedean data, making it completely incompatible with the continuous, flowing geometry of the observable universe. The spectral projection integral operates as the fundamental mining operation of reality. It successfully extracts the pure discrete code, but a secondary translation layer is required to actually make that code physically manifest. The objective of the second mathematical tier is translation. We have to bridge the extreme gap between the raw, jagged mathematics we just mined and the smooth geometry we interact with every day. This is handled by the J operator. It acts as a representation theoretic bridge, a mathematical compiler designed specifically for this translation process. The local eigenstate fed into the J operator is a rigid, non-Archimedean branching structure, known as a Brouhat-Titz tree. The operator applies a localized integral transform, mechanically scanning over the fields. This smooths out the rigid, disjointed branches into a continuous, oscillating geometric wave. In mathematical terms, this newly smoothed continuous output is defined as a stable, automorphic representation. By forcing this representation theoretic alignment, the J operator manages to mimic fluid physical geometry using nothing but rigid number theory. The J operator provides the vital structural bridge that grants abstract logic its first foothold in continuous reality. It takes the discrete mathematics and transforms it into stable physics. The final rendering phase relies on the macroscopic Lagrangian equation. This is the top-level operating system that dictates the layout of the observable physical universe. The function of this global field equation is to strike an exact mathematical balance between the continuous Archimedean data of our standard physics and the newly translated discrete non-Archimedean data flowing from the J operator. Successfully balancing this equation across the entire Adel ring generates a global topological anchor. It is the necessary mathematical tension that holds space itself together. But creating a universe on paper isn't enough. The theoretical engine must undergo extreme mathematical stress testing to prove it won't instantly break down into infinite physical states under pressure. The first structural defense is the kinetic Dirac test, designed specifically to prevent energy states from violently spiking to infinity. The test executes by applying the Vladimirov fractional derivatives directly to the newly translated field wave functions, calculating exactly how they react to fluctuations. This diagram demonstrates the control mechanism. The framework's strict underlying matrix logic locks any field fluctuations onto a rigid grid. When a wave attempts to spike, it hits an invisible upper triangular matrix ceiling and instantly flattens out. Because the fluctuations are locked, kinetic energy is mathematically blocked from diverging in the ultraviolet limit. Instead, it is forced to stabilize into a finite spectrum of eigenvalues. The second defense mechanism is gauge field regularization, which is deployed to control the massive mathematical complexity of prime numbers. The global trace norm of the field requires calculating an infinite product over all prime places. In traditional models, calculating infinite products leads directly to mathematical explosions. To resolve this, the system uses zeta regularization. It maps this infinite array of prime products directly onto the curve you see here, settling onto the precise convergence domain of the Riemann zeta function, which forces an infinitely complex calculation into a finite, usable value. These stress tests confirm the Lagrangian is an entirely airtight rendering system. By deriving our physics from strictly bounded topological constraints, the framework prevents the existence of mathematical infinities entirely. The Adelic program redefines space. It stops being an empty room where physical events happen. It becomes the localized cognitive language used to interpret a continuous influx of raw arithmetic data. In this paradigm, what we perceive as physical space is a macroscopic condensation of the underlying code, filtered through the observer's own localized field. This wondering occurs at a specific processing threshold, the Yang-Mills gap, located on the critical line of the Riemann zeta function at 23.67 MHz. This frequency defines the rate at which arithmetic data is translated into the observable environment. Within this gap, a Fourier-Mukai kernel decompresses zero-dimensional arithmetic code into the four-dimensional experience. The subjective passage of time is the literal mathematical work required to perform this data stabilization. Motion through space is the ongoing resolution of this data in the present moment, while the history of these states is locked in by the Arakelov metric. This ensures that every unique spectral signature remains a permanent invariant within the global ledger. The stability of this architecture allows it to function as a mathematical compiler for physical engineering. The first applied technology derived from this stability is the development of zero-divergence quantum computing systems. The mechanism operates by mapping the behavior of highly volatile quantum states directly onto the strictly bounded local patches of two-adic fields. By locking them into that compact topology, it creates qubits that are inherently immune to high-frequency phase noise, stripping away the need for massive computational overhead. The second engineering application targets physical construction, the creation of arithmetic metamaterials. The design methodology requires creating physical structural scaffolds, like the one shown here, that perfectly mirror the non-Archimedean two-adic branching logic. Matching the precise geometry of the math naturally isolates and dissipates chaotic structural stress throughout the material. By deriving physics from bounded topological constraints, the Adelic Langlands program provides a stable framework where the physical environment behaves as a computable, engineerable system.